Hello and welcome to Humans versus AI video 18, and this is a very important video. I think the last video, or potentially the last but one video. In this video we're going to terminate the training process at the point at which we detect convergence in the training, and we're also, and this is even more important, we're going to save the best model as we go. Not saving the model at the end of the training, we're completely dispensing with that. We're going to be recording the best model that we find as we go, which means when the training is complete, we'll have the one that performed the best throughout the training process. And this is also the thing we definitely need to do before we even contemplate the notion of hyperparameter tuning, because we need something that we can guarantee is going to find pretty much the best model in the run, the training run, so that we can compare that result to lots of other results we're going to create by tuning the parameters that we can tune for the training. If you don't know what I mean by hyperparameter tuning, we might get to that in a later video. So this is a really good video and it's actually quite quick and easy to do, so this should be a short one. I have a Patreon account, of course. Big thank you to those that do support my work. I really do appreciate it, and if you'd like access to the code, please do visit my Patreon account. Okay, let's go to the code. Right, so in order to stop the model training at a particular point and to evaluate the performance of the training at a particular point, we need to use something called a callback. So we're going to start this video talking about callbacks. So we're in the PPO file at the moment, and we're looking at the train model method. And what we're going to do is we're going to create something called a callback, and that's what this method is here. It's actually a class. We're creating an instance of a class. And I'll explain what this is in a minute, but just take my word for it for now. We're creating an instance of a class called early stopping. The class is called rollout early stopping callback, and we're going to create that in a minute, and it's not complicated. So we've got this thing called early stopping, which is a callback. We're putting it into something called a callback list, which is just here. So we're creating a list. Now the reason I'm creating a list, I don't actually need to, but I'm doing it because it's often the case that you have more than one callback. So if we want to have more than one callback, we can create as many of these as we like, and we can comma separate them in the list and add as many as we like, and they will then be triggered. So we'll see what happens with the triggering in a few minutes. So that's the early stopping callback, which again we'll talk about in a second. So by creating this callback list, we're able to then pass it into the model learn method, which we've been using all along for our training. This is what basically does the training, and this is where the list is being passed in. So this means, whilst the training is going on, whilst Gymnasium and Stable Baselines 3 are converging the PPO model, at regular intervals that we're going to define, we're able to stop and have a sneaky peek at what's going on. We're going to look at the training performance, and if it meets a certain criteria, we're going to stop the training to save ourselves time and CPU, but we're also going to record the best model as we go. Okay, so let's talk about what this is then. What is this callback? Let's go and have a look. We'll come to the parameters in a minute. So it's a class. We've created a new class, and it's very important to note that it's based on its parent class called base callback. Okay, let's just pause on that a minute. If we go to the top of the PPO file, we've always imported this since the very early days when we first introduced Stable Baselines 3, because I knew we were going to be using it. So this is new, but this is why we've been importing it all this time. We've got access to the base callback, which we need for the callbacks to work, and the callback list, which we've just used to create the list of callbacks. So that's the reason we've got that import. So let's go back down to the callback itself. So what the callback is going to do is it's going to run some methods at particular intervals. There are two of them in this case. So ignore the constructor for a minute. We'll come back to all of that. We've got onStep, which means the callback will trigger this method on every single step of the training process, which sounds very expensive, and it could be. But in this case, all it's returning is true. Continue to train equals true, is returning true. So it's super lightweight. This is required. You can't do without it in the callback. That's needed because that says callback's fine, carry on. The next bit that isn't required, but we want, is we want to say, let's have a quick look at what's going on at the end of each rollout, remembering that the rollout is when the model has been updated. So within our callback that we've created, this class that's going to run whilst we're training, At the end of each rollout, this code's going to run. And this is our entry point for looking at the quality of the trained model and to see if it's good enough to A, stop training, or B, save the model. So we're going to look at, before we go through this actually, we're going to look at some of the parameters that we're going to use to define when we're happy that we have converged. So we'll come back to this, just hold that thought. We've got the rollout end method that's going to be called at the end of each rollout. So hold that thought. We're now going to hop over to constants, where we've got the parameters we're going to need to define when we decide that we've reached a suitable point for us to save a model. So these are the new ones, the ones I've highlighted. There, that's new. It's not that complicated. The first one is record models threshold. This is a variable, you'll see in a few minutes, that we're using, which is basically saying when we get below the threshold defined here, we're going to start recording the models, which means saving them to file as energy collection model.zip. So when the episode lengths get below 300, when we see a model that has a certain performance that's better than the last model we saved, then save it again. So you're going to keep saving better and better models as we go. But that's the threshold at which we kick off that process. So no model saving is going to happen until we get below 300 steps in a given episode. Okay, and that of course needs to be tuned depending on what we're doing. These three are for the convergence, early stopping basically, for when we've converged the model. So the first one is the window size. So how many episodes are we going to average over? Because episodes can be a bit noisy. How many are we going to average over to then take a measurement of how well the training is going? And this will make sense in a minute when we look. I've currently got that set to 6. It's a little bit arbitrary. The bigger the number, the more smoothed out we're going to be. But we do want a reasonable size. So again, a tunable parameter. This one is the stop step threshold, which is basically saying how much variance within the window, from window to window, should we see in order to begin counting down towards terminating the training. So we want to see the variance in the episode lengths changing from episode to episode below this threshold. And if that happens for so many episodes in a row, that's where convergence has happened, because it's no longer varying. The training isn't having much of an effect on the episode length, and therefore we're in a good place to stop the training. So that's the threshold. So this is saying if there's more than 35 episode steps, game steps in the episode windows, so the variance between the windows is less than 35, and it happens for more than 8 episodes in a row, then we should terminate the training. And that's how we get to convergence, basically. Although actually that's not episodes in a row, sorry, that's rollouts. I've actually written it here. So there have to be 8 rollouts where we test this in a row, where the threshold is below 35, in this case, for us to terminate. So we'll see what all that looks like in a minute. But these are the parameters that define when we stop training. And this is the parameter that defines when we start recording our models. Right, hopefully that's clear. Wasn't the best of descriptions, but I hope that's clear enough. So let's go back to PPO then. I said to hold this in your mind. So our callback that runs routinely throughout the training at every rollout end. This is where we're going to do the recording and where we're going to determine whether we should terminate early. So first off, let's have a look. Well, we're going to be taking a window size and averaging over a given number of episodes, which means we've got to have a test here that says don't start computing the average over a window of episodes until the window of episodes has passed. Because of course, in order to calculate a window of episodes, so many episodes, we have to have passed that many episodes to look back at it. So what that's saying is make sure you've gone past 2 times the window size, where the window size is here. We've got to go 2 times that in order to start investigating early convergence or saving the model. So that's what that says. Then we calculate the moving average using numpy's mean over the window of episodes. Remembering that episode lengths is something we've been recording all the way through this series. It's an array of episode lengths. It doesn't matter what rollout you're in, throughout the entire training process, it's recording in an array the length of the episode each time the game is completed. So that's for the current moving average window and the previous moving average window. So in previous moving average window, you're going back 2 window sizes up to 1 window size in the past. So that's the last window, and this is the current window. So sticking with the current window then, we've got this logic here, and this is where we start saving the model. This isn't about convergence, this first part is saving new models. We say if it's below that threshold I mentioned, if we go back a minute, that 300, if the moving average of our episode lengths is below the threshold, then let's see if we need to save the model. So this is where we start saving the models. And all it does, it says, is the current moving average less than the best moving average? So the best moving average is first defined as this very big number, just to kick it off, up here in the constructor of the callback. So it's made a very large number to make sure that the first time round it always will be true. Then we go, yes, moving average is lower, so we've got a new, better model. So we save it using model.save. This is not new, we've seen that before. This used to happen at the end of the training process. Now it's happening with whenever we find a better model, which is below this threshold. Then we're updating what the last best moving average score was. So the next time, the next model will only be saved if we've found one that's better, that's beaten that. And we print it to the console to show we've found a new model. So basically, this is it. That's all the code we need to run through the training process. And then at the end of each rollout, just check whether or not we should actually save this model because it's the best result we've seen so far. The next part, and we're getting quite close to the end of this already, is saying this is the convergence calculation. The threshold, and we'll go back to where the threshold is, here, the threshold, if we have the moving average minus the previous moving average, if they are less than the threshold, then we've got convergence. And that state has to happen for patients. So if we go back to patients, which is a variable, we've got 8 for patients. So if we go back to the code, we're going to have convergence counter increment upwards. It gets reset if that isn't true. So it has to be continuously achieving that condition of being below that variance. And if it is, we increment up, and then the next section of the code basically says, aha, has the converged counter achieved more than patients? So is it basically 8 or above? And if it is, stop the training. And we do that by setting the continue to train variable, which is set to true here, to false. And this is where the on-step method I mentioned that has to be in here, this is where this will terminate the training, because the on continue to train variable will be set to false and training will just stop. That's how it works. Right, so that's the logic. Let's just talk about what's going on up here. All of this is just the constructor setting the member variables of this class from the variables in the constructor. So we'll talk about where they come from now, but that's all these are doing, and the same with the environment. That's all they're doing. So let's go and look at how we kick this off. We saw it before, but we didn't talk about it. So back up in train model then, we are passing the variables through simply from those parameters in constants. You'll see them there. We've got early stop window size, early stop step threshold, and early stop patients. And that's how it works. It's that simple. So let's see it working. Oh, before I do, I just want to draw your attention to tensorboard. The reason why we save the best model as we go is in PPO, it's not always stable. And this is a great example of that. The training has got better and better and better, pretty much minimized here, but then gone up again and not been very stable at the end there and actually started to climb. So this is a good example about why you want to try to save your best model as you go. There are much better examples than that. I don't think I've got one, but that's an example at least of the instability and it climbing again. Right, so if we run this, which I will do now, what I'm hoping to show you in the terminal is the process of seeing convergence eventually happening and seeing the model being updated and saved as we go. Now, unfortunately, the window does get cut off at the bottom when I'm recording. I think you're missing a tiny fraction, but this should still work. Let me just check the... Oh, train needs to be true. That would help. I ran it in evaluate mode by mistake. Okay. Try again. Right, what I'm going to do is pause the recording and wait until it starts training, because at the start, of course, nothing's going to happen. Right, so what I've just done there, having paused the video, is I've resized my Visual Studio Code window so that you can see the bottom of the terminal properly. And I've kicked off the training, and already we can see some of the outputs coming out that we're hoping to see. So the ones that have appeared so far are from the convergence code. So it's coming out from this piece here. So it's where it's detected that the window-to-window moving average variance is within the threshold that we've got set in the constants file, and it's starting to count upwards. But you can see in each line, it still says 0 of 8. That's because between each of these, it's actually not met the threshold and had to start again, which means it hasn't converged. It was a fluke. And that's the reason why we need consistency, because consistent low variance is a sign that we have actually converged on a solution. The other thing we're hoping to see at some point in the next minute or so is we should see the saving new model command, print statement, because that means that this piece of logic has run and therefore we've saved a new model. And in fact, on the left hand side, you can see energy collection model.zip. I'm actually going to delete that because we'll see that appear when a new model is saved. So we just need to wait now for that model to get created. Okay, so I just waited about 10 seconds after I stopped talking, and you can see down here the first instance of a new model being saved. Saving new model with episode average duration 276 and another one 234. So it will only have saved the new model. So this one has overwritten the one that it wrote before because it's better, or at least on average it's better. And up here in the file, we can see in the file list, we can see energy collection model.zip, which is the model that's been saved. So this file is getting overwritten over and over again when it finds a better model. We can see we got to 1 out of 8 there, where we've had 2 instances in a row, 2 rollouts in a row where it looks like convergence has been achieved. We've had more instances of saving new model. We're now down to 211 steps on average in an episode. So that's pretty good. And now we're down to 295. Oh, that's a big step down to 152. I happen to know that with this configuration, we can get to around 130, maybe a little bit below, and that's when the model works pretty well. Whether or not you get there does depend on a number of factors, and it has terminated early, so we haven't quite got to what I think it could get to. And that's the nature of the beast. That's the nature of the way training works. The convergence code has been triggered. So it's got to 7 out of 8 and then 8 out of 8, and it stopped training because it's detected convergence, which is quite correct. It is possible that convergence could have led to another drop. So if we go to tensorboard, we'll have a look at what that looks like. PPO6 by the looks of it. Is it PPO6? Yep. So let's have a look. There we go. So we have converged, and it's at this point down the bottom where it's stopped. So if I zoom in on that, there we go. So it's those last few bits where it's decided, yep, we're not really varying enough to continue to train, and we've stopped. Now, in my view, perhaps maybe my convergence code is a little bit lenient, because I think that could have gone down a little bit more. And like I said, from previous examples, I'm pretty sure it can get down to about 130. So this is an example of where I'd probably allow it to converge a little bit longer. And you can see here on the reward, it's continuing to climb. So I think it could have gone a little bit higher. So the convergence did stop a bit early there, but you can see why it's important that it did. We could have carried on to 1,000,000 steps if we didn't stop it eventually. So slightly early, but you get the point. And as it's gone along at every little minor dip, it's recorded a new model. which means the best model it's recorded achieves an average of an episode duration of about 150. So not optimal. I'm pretty sure when we run evaluate on this, we're going to see a suboptimal solution, but it should still work. So let's have a look. I expect it to be quite a wandering AI player, but still working. Too bad. Not too bad for quite a large grid. Now it's got stuck, and this can happen. Oh no, there we go, it's come out. Sometimes it can get stuck in between energy points if the energy distribution is equally balanced. There we go. So as you saw there, it wasn't a perfect run. In fact, it took 205 frames to win, even though the model that we have saved could achieve around 150. But of course, we've only run it once. There would have been tens of episodes that created that 150 metric. So we'll see what it does this time. I'm expecting it to be better, just because I think 200 was quite poor, given the model's results from the training. This looks like it's doing better. There we go. This one was 146, which is more in line with what we would expect. And actually, that's one of the reasons I wanted to create a machine learning based computer game, because I like the fact that it's different every time. It's not easy to predict, and therefore you get some very interesting results. Right, that brings to an end this video. It also potentially brings to an end this series. I might do another video on how to tune hyperparameters just to round off this series. But if I don't, thank you for being part of this journey, and I look forward to seeing you in my next series, which will be hosting this video game using Django as a back-end web framework and Angular as a front-end web framework. And we're going to host the game with the Raspberry Pi being the server and the client, the game being played by the user, being in the browser. So hopefully you can have a go yourself. Thanks again, and I'll see you in the next video.